this map of 50 essential algorithms, right next to divide and conquer in the design strategies tier, we find algorithm number 10, greedy algorithms. The core idea here is extreme impatience. If a system makes the single most attractive choice available right now at every step, without ever looking back or rethinking a decision, will it eventually reach a mathematically perfect outcome? That question sits at the center of computational design. It represents the raw trade-off between the desire to calculate a flawless global optimum and the very real demand to get a fast, usable answer immediately. In 1951 at MIT, a graduate student named David A. Huffman was given a choice by his professor: sit for the final exam or write a term paper solving an open problem on creating the most efficient binary prefix codes. What Huffman didn't know was that his professor, Robert Fano, had been wrestling with this exact problem alongside the legendary Claude Shannon. Their approach was to divide the data from the top down, a method that was solid but couldn't guarantee optimal compression. After months of failing to improve on their work, Huffman realized the answer wasn't to start at the top. Instead, he built the data tree from the bottom up. His rule was simple: relentlessly merge the two least frequent symbols together, over and over, until one tree remained. By ignoring the big picture and focusing strictly on the single smallest pair in front of him, Huffman proved that a short-sighted, local rule can flawlessly construct a globally optimal architecture. That short-sightedness is the defining mechanic of a greedy algorithm. You take the biggest coin that fits, you pick the shortest path available this exact second, you commit instantly, and you never backtrack. For this impatience to yield a perfect result, the problem must have the greedy choice property. This dictates that a globally optimal solution can be reached simply by chaining together locally optimal moves. It also requires an optimal substructure, meaning the best solution to the overall puzzle is completely composed of the best solutions to its smaller subpieces. When a problem passes both of those strict mathematical tests, the greedy strategy transforms from a fast guess into a precise, optimal solution. We can see this in action by looking at this diagram of Huffman's code. We start with a set of symbol frequencies at the bottom, like A at 45 and F at 5. The algorithm executes its single rule. It grabs the two lowest frequencies, 5 and 9, and merges them into a single node of 14. Then it grabs 12 and 13 to make 25. It repeats this exact local choice until everything merges into a single root node of 100. The payoff for this bottom-up build is that the most frequent symbol, A, sits highest in the tree. It receives the shortest, 1-bit code, compressing the total message perfectly. But watch what happens when we apply that exact same impatient logic to the traveling salesperson problem. This diagram tracks a greedy attempt to visit a set of Canadian cities. Starting in Ottawa, the algorithm looks for the absolute closest unvisited city and hops to Kingston. Then Toronto is the closest, then Sudbury. Every individual step makes perfect local sense, but because it never looked ahead, the algorithm traps itself. To finish the tour, it's forced into a massive, punishing leap from Montreal all the way back to Ottawa. The greedy approach to the traveling salesperson problem is incredibly fast, but because it routinely misses the shortest route, it exposes the inherent risk of algorithmic impatience. The entire reason engineers accept that risk is speed. The greedy strategy's efficiency comes entirely from making a single pass through the data. In the Python code for this nearest neighbor solver, the logic is stripped down to a basic loop. It simply scans for the closest unvisited city, immediately appends it to the tour, and repeats. At scale, that simplicity pays off. A greedy script routes 2,000 cities in under a second. A brute force attempt for those same cities would calculate massive permutations, taking longer than the lifespan of the universe. The true value of this code is that it nigh passes computational impossibility. An extremely fast, approximated answer is infinitely more valuable than a perfect one you can never actually compute. Greedy algorithms win for compression and shortest paths, but they fail making 6 cents from 1, 3, and 4-cent coins. Greedy grabs 4 and 2 ones, missing the optimal 2 threes. Use greedy only when guaranteed, otherwise it's a heuristic. To solve those overlapping problems where a greedy guess traps you, you need an algorithm willing to exhaustively remember every possible subproblem, which is exactly how dynamic programming takes over. You can find the underlying code and context for all of these approaches in Imran Ahmad's 50 Algorithms Every Programmer Should Know.